Okay. So we're going to use some of this class for continuity equation. The continuity equation of the current is based on the principle of conservation of charge. Charge can neither be created nor be destroyed. So, consider, okay, we're going to read through this because this is very important. Consider a closed surface with current density J. Then the total current I crossing the surface is I equal the integral over the surface of J dot ds. That should be your Bible verse by now. So the current flows outward from the closed surface. It has been mentioned earlier that the current means the flow of positive charges. Hence, the current I is constituted due to outward flow of positive charges from the closed surface. Logical so far? So according to the principle,
Can I repeat that, sir?
you have to follow it, follow it. The current flows outwards from the closed surface. It has been mentioned earlier that the current means the flow of positive charges. Hence, the current I is constituted due to the outward flow of positive charges from the closed surface, S. So according to the principle of conservation of charge, there must be decrease of an equal amount of positive charges inside the closed surface. In other words, charge a flow out. And since you can't create charge, that means wherever it is flowing from, it is decreasing by the same amount which is leaving. Hence, the outward rate of flow of positive charge get balanced by the rate of decrease of charge inside the closed surface. So let's Qi be the charge within the closed surface. Minus dq dt, that is the rate of decrease of charge inside the closed surface, is equal to the current, which is the flow of charge through the surface. This equation is what all of this says. Charge decrease within the closed surface equal the current that flows out. So, this is what is known as the integral form of the continuity equation. The negative sign in the equation indicates the outward flow of current from the closed surface. Said that already. So equation 2 is indicating the outward flow of current. Say all of that. If the current is entering the volume, then this would be negative. This is flowing out. So if it's negative, it's flowing in. It's minus I. And this would be positive. So that's the integral form. Now, the differential or point form is this. Del dot J dV is I from this morning. Which is equal del dot J dV is minus this from here, from your equation up here. Right? But Q is the integral of rho dV from way back when. So if we go through the math here, go through this math. Get to this, which is the point form. All right, so go through this and tell me if you follow it. This is just math.
So yes, sir, I think I'm following, sir.
So, sir,
Yeah,
the T is, the differential T is in respect to time?
that's correct.
Okay.
Rate of change.
Sir, can you with the divergence function again? I don't. It's a new topic, so not following how it applies.
Oh, what did I do? What did I do?
I follow, sir.
Huh?
I follow.
Yeah. Well, I'm gonna know which button me just touch.
Oh, sir, I zoom in, sir. You have to just zoom out, but the minus sign.
Closer to the center, sir. That bar. Yeah.
Okay.
Give it some more clicks, man, sir. Give it some more.
What was that question again?
Oh, yes, sir. With the divergence function. Yeah, I'm saying that they're not following how it applies.
So, what was the divergence theory again?
Sir, I recall it being something about, well, from the text,
I hear something, you know.
it said from the text, it is the limit with respect to delta V of the integral
Delta
of
V towards 0.
the surface
Integral of
area over the volume.
So all we did was substituting this for I. And that is from the divergence theorem that we did last week or week before. That's straight substitution.
Oh,
Get it?
all right, so
So this is the point form or differential form of the continuity equation. So for steady currents, which are not a function of time, that means this is 0, del dot J equals 0.
sir, could you use an example with the above scenario? So, maybe a circuit or something.
Not quite understanding now.
Right, sir. So I get that J is normal to the direction of the current through the surface. But I just not, I don't see how we do the divergence thing. I don't get how the function. But I guess mathematically speaking, it makes sense. But
You just have to review the divergence because it's a straight substitution from the divergence theorem.
yes,
This is a straight substitution. We don't do anything. Just substitute this for I or minus I. So you just have to review your divergence.
yes.
All right. So we said 20 minutes. So next week we'll pick up at conductors and the Ohm's law and all of that. So page 56. There's no problem set again on the thumb drive. No? So okay. So this was the one that we did last week, right? That you were supposed to do for your homework.
Sorry,
Sir, I think it was
Was
2.35.
It wasn't that one, sir. It was 235, yes, sir.
Mm.
All right.
Oh, sir, you said you were going to explain how you derive the formula that you would have put in, that you put in DS.
The formula that for 235.
Yes, sir.
All right. So let's read the question. Okay, by the way, anybody solved it?
As in,
Sir, made an attempt.
made an attempt, sir.
Solve it.
But
yes.
like I said, sir, I don't deal this more well.
Sir,
Hmm?
35 attacking, sir.
Yeah.
Rough, sir.
All right.
Sir.
Yeah.
Alright. Sir, made a carried through with it, sir. Solve it, sir.
All right. So tell us what you did. Let me put up the solution.
I was way off.
Is that what you got?
Yes, sir.
All right. So walk us through this then.
Alright, sir. First, use the equation for Gaussian surfaces.
Mhm.
It says the enclosed charge is equal to the contour integral of the flux density.
Of D dot DS.
D
So
dot ds.
this supposed to be a circle and this supposed to be a dot.
Yes, sir.
So Q enclosed is the integral over the closed surface of D dot DS, right?
Yes, sir.
Okay, continue.
Sir, because that symbol there, it look like a pitchfork thing. I don't recall which one it is. It's equal to,
Flux.
yeah,
What?
for the flux, that Greek letter is equal to the,
Which Greek letter you're talking about?
all right,
Flux, the one for flux.
Which Greek letter?
all right, sir, in,
As in, sir, we don't know its Greek
I
name,
think
sir, but we
it's
know.
no. It's the one for web or
Somebody says phi. No, it's phi?
phi.
No, you should find the P.
No.
You're not talking this?
No, sir. At the fuck him attack, sir.
Huh?
At the fuck him attack, sir.
The
Which
flux,
phi?
sir.
Sir, so only like what Aquaman would I use, sir?
Tell me where to go with this.
All right, sir. So the differential volume is equal to R squared. Differential volume is equal to R squared sine theta d phi.
No,
AR for
before we do that, I would just like to know what you call in a phi first.
It's psi. Yeah, it's psi. It's psi. Not phi, it's psi.
Is it here on this page?
No,
No,
sir. No, sir. But
Oh,
it's in the formula that we got.
oh. So that's the same thing as flux.
Yes.
Okay. All right. Okay. So here we are. Bring me through this.
all right. So the contour integral of d dot ds is equal to the integral of dr ar times r squared sine theta d theta d phi ar. So that's the dot product between them. So after working this, comes down to what you have as 4 pi r squared dr. So
All right.
then you find Q, you find the enclosed charge Q, what's called QENC, by plugging into this equation, the above the where you have the cursor. Integrate it with respect to between the limits of phi equals 0 to 2 pi, theta equals 0 to pi, and r equals 0 to r.
Mhm.
Now,
That's this.
because in the question, yes, because in the question it was given that rho v equals rho o or rho naught r over a,
That's this.
yes, you would plug it into the equation thing for psi, where it has the integral of rho v times dv.
Mhm.
So you would get this equation where it says gs1 equals this, integral of rho v dv equals rho o over a. The r from rho over a multiplies by the r squared, they get r cubed. And you get dr integral between 0 to pi sine theta d theta, integral between 0 to 2 pi d phi. When you work it out, you get this value. Pi rho 0 r to the 4 over a.
Mhm.
Then it is given that the enclosed charge is equal to 4 pi r squared dr for a Gaussian surface. So in order to get dr, you would solve for dr by transposing 4 pi r squared to divide the enclosed charge. So you would move from the line where you have GS1 to the next line by dividing this pi rho naught R4 over A by the 4 pi R squared.
Right. Okay. So we just assume that everybody got that because nobody interrupted or asked a question or anything.
I mean, from the start where I said, no,
Huh?
nothing, sir. Continue, sir. Continue.
Oh, so that was for the limits described when R is less than or equal to A. For the latter part now we have to find the Gaussian surface for the limit where R is greater than A. You would use a similar approach to the equation before, except you would be integrating now from 0 to R and then from R to A.
Right.
So is that double integration would that be there then, sir?
Where?
When you say you integrate from O to R and then from R to A.
You
Not
would,
a double. It's two separate integral.
Oh, okay, sir.
This is a good one. a thick walled spherical shell with inner radius this and outer radius this has an evenly distributed 12 Coulomb charge. No, this is same plot, so this is it's gonna be a MATLAB thing.
So when to use MATLAB for this course as well, sir?
No. No. You don't have to. All right. All right. Let's try 237. All right. When we time out, I'll just restart it. So go ahead and try 237. Uh, Anyone make any progress so far?
Define progress, sir. Try thinking us, sir.
Yeah.
Try.
Sir, question for this one, we would have to find the Gaussian surface.
Hmm?
We would have to find the Gaussian surface density of the length, the bottom of the coaxial cable on the top.
Yeah.
And then after that, we would have to do what? Like multiply them together?
Let me start. No, man.
You wouldn't minus them since it's Q. One is
No,
positive
no.
and one is
No,
negative.
no, no. No, you're gonna have two answers, eh?
Oh, answers.
All right. Let me get out my pen. Because you got, this is your coaxial, right?
Yeah.
So you're actually gonna have three answers.
Oh, for the inner, for the outer, and then when them together.
Because right here now, what them say that is what? A,
Yes, sir, the radius is A.
that's A. And then people choose to use Waka to B. All right, so the inner radius is A. So this is A. This is B. Right? Them say the outer conductor
The
goes.
surface on a C, sir.
Hmm?
The one on the other side, the outer ring is C, from B to C.
Yeah, so we're so B is between here, right?
Is outside, yeah. B and C is
Yeah.
outside.
It's outside A. Yeah, C is outside here.
Yes, sir.
Oh, sir.
Hmm?
I was saying I think it would be 4 because you would have a outer coating and then you'd have the metallic part and then you'd have the lagging and then the wire.
The lagging?
No, man, you have one in the inner, inside the outer radius. One between the inner, the outer, outside of the inner radius and the inside of the outer radius. And one for outside the outer radius. Now let me think. Let's see what they did. So you have a positive charge is distributed throughout a meter length of the inner radius, inner conductor. So plus Q. And a minus Q that is evenly distributed through a meter of the length of the outer conductor. Right? So we want to derive the flux density for all rho. So then we start off by having our valid Gaussian surface. So charge enclosed equal the integral, the closed integral of d dot ds. Right? So define your Gaussian surface. It's a cylinder. So it's on the surface of the cylinder. So it's 2 pi r times L. That's the surface area. Remember, you have your flux density, D, is only in one direction, radiating outwards, right? So that's your flux density D. So D dot ds is nothing more than 2 pi. The rho is what we would call R, right? So it's 2 pi rho times L, which is the length, times d rho. Everybody see that?
What was that again, real quick, sir?
I not quite get the row part, sir.
What's the surface area of a cylinder?
That is the integral of the surface area.
So
E dot ds.
Hmm?
So
What's the surface area of a cylinder?
2 pi r.
As in the formula, sir?
Yeah.
2 pi RH plus 2 pi R squared.
So the surface and the volume is different.
No, remember, you know, we don't need to consider the top and the bottom because we don't have any flux density in that direction. So we are only considering the side of the cylinder.
Oh, so just 2 pi RH.
Okay. 2 pi RH. So it's 2 pi R is what we call rho.
Oh. Oh.
And H is L.
Which is the 1 meter.
Hmm?
Which is the 1 meter.
Yeah. Mm-hmm. So D, we only have D rho. So D dot ds is just this. You get that?
Yes, sir.
Yes, sir.
So then, for rho less than A, right? Rho less than A.
what's that, sir? Rho V, sir?
That's the volume charge density.
Oh,
This is rho V, different from this rho. This is your
okay.
volume
Wait, what you just said, sir? Different from what, sir?
from this row in up here. This row is what we teach from the notes as R.
And the next one is the
Volume charge density. So the volume of a cylinder is pi r squared times h, right? So Q, which is your total charge, divided by your volume, gives you your volume charge density. Yes, I know.
Yeah, man, sir. That makes
Density,
sense.
just
I don't
transport
know why I'm
force for the
integrated
density.
first.
Then you charge right? Because, okay. Remember, you have three different rows that you are going to account for. So your volume charge density times whatever, because your volume is gonna change depending on where you are, right? So this is your integral for your volume. Rho V is a constant. Here is rho V. So for the inner cylinder, for the inner conductor, this is the equation for your charge.
So sir, for Q1, the 0 to rho would be the 0 to A, sir?
Yeah,
Okay.
right.
So you don't have a problem if we use R instead of rho when we're talking about radius, right?
No, man.
Thank God.
There's different textbooks. Some people are anti-vaxxers, some are vaxxers. Some use R, some use rho. So from there, all you need to do for rho less than A, right? This is what this work out. For rho between A and B, if you notice, there is no charge between between A and B. So whatever it is, at A, it's gonna remain that all the way up to B. No,
So what's D rho stand for against there? That's the
that's the flux density. But remember now, for a cylinder, this is your flux. So the D rho is the flux, the radial flux.
and phi is just like the flux of like just any random any shape we get.
Hmm?
I was saying phi is just the volume charge density of like just any shape we get.
Any shape.
Like if we get a cube, sir, or a sphere, or a cylinder.
Right. I mean, if you get a cube, it's gonna be in the AX, AY, and AZ. But for the cylindrical, for the cylinder, you only have in the row. So both for GS2 and GS3. You just, actually you're correct. We have a GS4 too. But all right. I think this is pretty straightforward. GS2 and GS3. Anyone? So GS2, GS4, GS4. I'll show you already. Whenever I want to show you GS4. But GS4, this is the story. You have current going, positive going in the inner conductor, and negative going in the outer conductor. So the net charge is 0. So Q enclosed is 0, so you not even have to work that out.
So JS1 would be the conductor though.
GS1 is from 0 to A. GS2 is from A to B. And GS3 is from the inner surface of the outer conductor to the outer surface of the outer conductor. And GS4 now is outside the two conductors.
So you couldn't make a schedule say get for follow your assessor.
I always have to give me the hard job.
Sir, what I did, I just Google a coaxial cable and use that as a guide. So I'm not sure if you did that.
You know what?
I just Google search a coaxial cable and then I just use the layers to describe A, B, C, and D.
Oh, what's your name again? Tell me. Now go make your show me.
Delroy Thompson. Sir.
Oh, I see, man. So, I'm gonna make you the host now. So put it up though. You're now the host now. No, man, but you know. Well,
Sir, all right, so I call the copper wire as the A and going outwards, all right, to Gaussian surface 1 and insulation would be surface 2. The mesh would be surface 3 and the outside as surface 4.
This.
Don't worry, public, I'll search up cross-section here, cross-section. Coax cable, cross-section.
You have one? Beautiful. This is what I want to see now. So there you go. So A is the inner conductor, right? From 0 to here. B is inside of here.
The second picture would have better.
Which one?
That one. That's second.
This one? This one? Oh. Here. Aye. There
Yeah,
you
the
go.
one with the red.
Yeah, man, I like it. I'm going, man.
But it even have the radius A, radius B, and radius C that we use.
Exactly. So the only thing, you see, between A and B, right? Q doesn't change because
I mean, yeah, we'll have to be at.
eh?
No, sorry, sir. I'm just realized the Wi-Fi did chip out. I just come back in.
Okay. So from whatever you get at A, it will be the same thing all the way up to B because the enclosed charge does not change. No, between B and C, you have your enclosing, your plus Q plus a portion, depending on where you are, of the minus Q. Outside of C now, you are enclosing plus Q and minus Q. So the net charge enclosed there is 0. Get it? All right, give me the host now. We'll find our next one. You give me back?
Oh, yes, sir.
Sure.
Yes, sir.
Okay. So let's. Okay, this is a beautiful. I'll just give this question for you. This.
Sir, I'm not seeing anything on my screen.
Nothing coming cause that. Nothing coming cause that.
Anybody else seen anything?
No.
I'm not seeing anything either.
Hold on. I see it now.
Yes, sir.
Okay. When I get back the hose up, I believe I didn't go back and share screen. All right. Several times I've given this problem in an exam. See what you can do with it. Where's that? What am I? Yeah. Let's do, yeah. All right, cool. Yeah. But, yeah, man. Mhm. Cool.
As far as I'm concerned, since we met you people 500 years ago, look at us. We've given everything.
Okay. Who have something to talk to me about?
So for part A, sir, you just plug in the values into the equation, sir. Seeing as though it just want the charge density at well,
Okay. So this says what?
you use the divergence, sir.
All right, del dot D equal rho. So it's just plug and play, right?
I thought that was the case, but I was wrong.
Then I this one.
Yeah, no, me do something else.
But you explain it right now.
Mm-hmm. So now tell me say you know the right thing and you go do the wrong.
Boy, sir.
Because what you just said a while ago was right. So you what else could you do?
Got me plug the wrong things into the wrong value, into the wrong equation.
So go on, what you do for part B?
Me never reach too far in the part B, sir, because me, rain start here, so me end up come back a bit late. But when did I try set up the Gaussian equation, but I didn't do it like that. I thought I keep messing up the Gaussian equation. I keep putting the volume into the surface area. So instead of the top plus base plus left plus right plus front plus back, I end up with L cube for this. So,
All right. Everybody understand why this is the two side of the divergence. Integral of d dot ds equal to integral of del dot d dv.
Yes, somebody didn't understand it up to that point. My notes.
So there it is, straightforward.
Mm.
and everything.
I think me see it, sir. I think me see it.
Um, yeah, I'm see it, sir. I mean, they wonder why how them specify how them decide which part of the equations they use, but them realize
There you see. So So this is the left, this is the right. All right.
Yes, sir.
Sir,
Yeah.
was there any other ways to solve the question? This,
Now, man,
oh, all right. So,
I just the two side.
all right.
Well, you invent another way.
Sir, why make it so, sir?
Joke that way. We call it that. It's a lot for the day. All in a day's work. This COVID thing, I really I get big, you know. So I eat. I'm big already. All right, next week.
Don't know, sir.
All right, sir. Next week, sir.